Hi, this is John McGill. I am recording another lecture for Operating Systems class. This is Chapter 2 and 3. So we're going to talk about memory today. And before a CPU can actually run or process any information, it can only get to that information if it has an address. And usually those things are the accumulator, the program counter, index register, stack pointers, and the status register. And we're going to talk about some of those things. We've already talked about binary numbers, so that's over with. If you haven't listened to that lecture, please go back and listen to the binary numbers so you kind of understand binary numbers. But as we do this, we are talking about addressing, and we're talking about addressing our memory. So we have RAM here. And it's addressable in binary numbers, starting with all those things that we just talked about, and everything is addressable in binary. So the first thing we have are what are called zero pages. And zero pages are close and easy to get in and out, and many programs start there. But we have zero pages that are there. Now, as we start talking about this, I'm really talking about a CPU that is single task and single user. And we'll talk about those other devices that are multitask, multi-user later on. But for now, we're going to talk about this to make it a little bit easier. So we have zero pages. Oftentimes the beginning of some operating systems are there. We have a stack that needs to be and have space on the RAM as well. We have, and the stack that I talk about are things that can be put in and stored, and every time you push something else in, everything moves down and additional information is stored there. And then you can pull off whatever's on top. The best example I can give you is your calculator. It's a picture of a calculator. And many of your calculators have memory. So as you punch in a number, do some calculation, you get a conclusion, and you can actually push your memory, which is like pushing it onto a stack. Later on, when you're done, you have completed some other calculations, you pull it off the memory and into your calculations. So that's what you're doing. It's a stack. We have user programs that are added. Anytime you run a program or download a picture or are running editing a picture or writing a document, all those things have to be in RAM in order for the CPU to get to it. We have screen memory. So as you see things on the screen, those little bits and bytes have to be in memory somewhere so that the monitor can read this area of RAM and display it. If your mouse moves, it has to display in bits and changes in RAM so that the screen can see it. We have mapped I/O devices. So when you press a keyboard, somewhere in here in memory, at a certain location, the letter A has to show up, or the ASCII representation of the letter A has to show up so that the CPU can read it and calculate it and then show it on the screen. We have operating system as well. Everything that the operating system has to be loaded into RAM and to be able to run from the RAM so that the CPU can access it all through memory. So we have operating systems, mapped I/O, we have the screen display memory, we have user programs, we have stack, we have zero pages. It's a lot of stuff, and that's why Vista, for example, took 2+ gigabytes of memory, whereas Windows 7 and Windows 8 really only takes 1 gig of memory to make it work, because Vista was very heavy, and especially on the screen display, had a lot of extra stuff. So let's talk about the stack real briefly. The stack, as I said, is often last in, first out. So, or first in, first out. They can be used for a number of things. It could be the next instruction, could be put in and come out. In the book, it talks and has a script of how to write a program to push something in memory and pop it back out. And fortunate for us, we're not going to go over that. That's much more information than we need. But they can use for operating systems, user software, anytime you need a little bit extra, or to save a bit of code and pull it back out again, we can do that. We have our RAM here. And many of you are programmers, and many programming languages force you to declare a variable. And what are you doing when you declare that variable? You are setting up an addressable memory space that you can always get to that. So you declare this variable. Sometimes you have to tell it what type it is, so you know how big and how much memory to save, so that you can pull that back out again. And you assign that to a word so that you can find where that is in memory. Oftentimes there's interrupts and errors that happen on the CPU, and it takes that handler to decide what to do with that. That handler is often a subroutine. So as you're working along and there's an interrupt or there's a program that has to happen, sometimes it has to go to a subroutine, work its magic here, and then come back. How do you get that information back and forth? Once again, you have a space in memory that has an information. So it stores in memory, and then this piece can read it as well. And we see this a lot in system calls, in different programs. These could be functions. We can call these classes. We can call these libraries. All these things are different things that we call these subroutines. We have buffers, which is often first in, first out. So we talked about how the USB, if you've got a computer and you've got a USB plugged into your computer, if you save something, you're really saving it to a cache or a buffer. And it may not actually flow into the hard drive or the USB drive until it's forced to clear that buffer. That's why you want to make sure you not just pull out the USB, but you eject it carefully. Sometimes we use buffers reading and fetching data from a disk, and sometimes as interrupts on a CPU. Now, an interesting thing on CPU is we can have interrupts that are synchronous, meaning while this interrupt happens, the CPU has to go off and do something else, or has to read some location in memory. And in the old days, what happens if that memory was blank or there was an error there? Well, if it was synchronous, the CPU just had to wait. And that's when you saw the blue screen of death or your computer just hang up. Most of the time now, most things are asynchronous, and it can go on and do something else. It can slice with other things, and we don't see those issues. So it's gotten much better, thank goodness. Now, there is such a thing as direct memory access. If you look on your motherboard, you may see trace lines from different places, and those are called channels in DMA. So let me explain DMA. So you have your RAM here, and you may have another device over here. And my students in class didn't think I did this very well. So we'll see if you think it is. Yes, so you have speakers. Okay, I'll label it. And you're playing the music. Okay. So how much does your CPU need to handle this traffic? You have an MP3 song that's playing. Does the CPU need to generate all the interrupts for that music? It wouldn't be very efficient, and it would take a lot of your CPU time. So what the DMA is, it means that it can go directly to your hard drive. And it has a channel that will read directly from the hard drive. Now, on your screen, you have a player, and that player will often have the stop and the reverse or the play on it. So this is the only thing that really interrupts and affects the CPU, but the actual song itself is coming from the hard drive, some space in the hard drive. Yes, at some point it may have to do some conversion, but the card that's in your computer, your sound card, has chips and processing on it. So your video card and your sound card has enough chips and processing on it that it can do that conversion for you. It can do that conversion, it can play and make the sound play. So we have a great way of doing DMA. TiVo and other TV recording things do exactly this. It doesn't go through the CPU, it goes directly to hard drive. And thus the hopper can do seven channels, right? Let's talk a moment about Bootstrap. Bootstrap means as you start up your computer and as you pull on your boots, poor picture, you often have bootstraps that you use to pull on. So there's a bootstrapping. So we have BIOS. This is a burned in chip on your motherboard, and it's called Basic Input Output System. It's a program, sometimes called firmware, that's burned on your chip on your motherboard, and it has a basic structure to get your computer started. So as you start up the computer, the BIOS system starts up first. First thing it does is run a POST, which stands for Power On Self-Test. Is my keyboard connected? Is my CPU there? Do I have RAM? Do I have chipsets right? And it goes through a quick post, and then it looks for some information. That information that it's looking for is stored in CMOS. So you have another chip on your motherboard that's called a CMOS. Usually this has a battery. It's supposed to be a battery that adds power to this and keeps the information there. So this stores information about what hard drive it is, what kind of hard drive, what do you want to look for first. It stores time, and it stores a number of information. You can even put a password here on your BIOS. Now the problem is if you forget that password, the computer won't even get past this. It stops and waits for that password to happen. But that's easy to overcome. You just take out the power supply and the password is cleared out and CMOS is cleared out. Yes, sometimes the battery wears out and you have to replace the battery, but that's a really old computer then. So one of the things that's stored in BIOS is where to look for. So that may be your hard drive. Where's the hard drive? And which hard drive should I look at first? And when it selects it, it says, here's the sector 1. You should go to sector 1 and you will find what's called a bootloader. Different operating systems use different kinds of bootloaders. In Linux, we use grub oftentimes, or in Windows, it's ntloader. And it's a small program, so BIOS hands it over to the bootloader once it finds it in the boot sector, and then the bootloader has other variables stored on the hard drive that says, where is the OS? And it could be on another hard drive or the same hard drive, and it's in sector, let's say sector 7 or wherever it is. And it says where it is, and so the bootloader is in charge of taking the OS and loading it into RAM. Once it's loaded into RAM, it then turns over and says start running the OS, and then the OS takes over and we go from there. So a cold boot is just as what I've described here. You start from BIOS, computer isn't on, it runs through post, and it keeps going. A warm boot is when you have the computer already on and you're just restarting it, and it's just starting at the bootloader, not going through a whole post and BIOS again. So that's the difference between a cold boot and a warm boot. So the next thing is, now that we have described what a single task and CPU is, doing one thing at a time, we can have multitask and multi-user devices. Windows, let me ask you the question, is Windows Is Windows 7 a multitask or a multi-user device or operating system? And the answer is no. Windows was developed so that only a single user can sign in at a time. However, Linux and Unix was described so it's multi-user. So many people can sign in at one time and do different things. What that means, though, is now we have to share resources. We have to share processes between different users. We have to share memory between different users, and devices and file systems and network, all between different users. And the kernel has to manage those so that one process can't get confused with another person's process, and devices and memory all has to be separate. Now, Windows was developed specifically for sharing, so as a single user. However, Linux was developed to be that multi-user, and thus inherently Linux is more secure than Windows. Thus Unix is more secure than Windows. Thus, since Mac OS is a version of Unix, it is inherently more secure than Windows. Now, that doesn't mean it is more secure, just the way it was designed. Which means as users are signing in differently, it's important that we have authentication, either a password. That means that as you use your system, the things that you create, you have ownership of, and you can share that with other people. Now, which means most operating systems now run under privileges and security. So you have to have authorization. Once you have authentication, just tells who you are. Authorization tells you what you can do. Most computer systems today use and run in two modes, and only two modes: user mode and privilege mode. Doesn't matter what rights you have. For example, Vista and Windows 7, that was the problem with Vista. you are running in user mode all the time, and only when you have something that you need to do that takes privilege mode will that UAC control come up and say, yes, are you sure you want to do this? Or do you want to cancel out of this? Linux is very popular with this because you're always in user mode, and only when you need to do something privileged do you then go to the administration and have to sign in and say, yes, I want to do this. The advantage of this is if a virus is coming in on Windows XP, if you were the administrator, you were always running as administrator. Virus would come in and it would run as you and as administrator. In this way, you're all running as user mode, and a virus comes in, it only gets the permissions you have. It never gets the privileged mode and administrative rights. So this is a big security issue and solves many problems. So as we do this, we've got that two-mode operation. We have to separate the tasks. Some privileges, some operating systems need that administrative rights. So oftentimes it'll boot in privilege, then switch to a user mode. This is called forking. So we'll see that in many programs. Linux, for example, starts an init program, and every process is forked off that init process. So if the init process dies, the whole program and computer reboots. So we have to share memory, both I/O and memory for the program. We have to segment that into different users. We have to time share our CPU and sometimes return that control to the system so that it can do privileged things. So we have many layers that we have to take care of. So what this means is user 1 has a space in RAM. It has a virtual input-output system. So we talked about input-output memory location. It's still there, but we have a virtual system. So the kernel has to be aware that I'm going to look here if the keyboard is pressed for the letter A. It has to look for the user B or the second user and look to see if they've pressed the keyboard, or the second or the third user, the same thing. So we have space and it's separate. Each of these is now separate from each other and they don't meet between. So user 1 has a virtual I/O, a separate program, separate stack for all the variables, input, output, and each has their own screen area as well. So we have to keep that separate. That means this kernel has to be very much different and up on making sure that each of these things are separate. Now that means that the kernel itself, we really can't directly connect it, so we need some kind of user interface to get to it. Oftentimes that's what's called the command line interface or a shell, and we'll get and see that in Linux as we go forward. Now there are some programs that need to have certain resources and we need to share those, but sometimes they're not run as a regular user, but they're owned by the system itself. These are called services and called daemons. Some people pronounce them demons. Doesn't really matter how you pronounce them. It's like Linux. Linux can be pronounced Linux or Linux. Doesn't matter how you pronounce it, it's all the same. So here's a couple of systems, services, or daemons that are running. Linux always likes to add the D to it, so you know it's a daemon. Syslog, anytime there's something written to the event log, the syslog is running to do those writes. When you convert a name to an IP address, so you can go out on the internet, the name D service needs to be there. The mount D is whenever you plug in your USB or CD-ROM, that needs to be there. So it can mount those things. So those are running and owned by the system, not by a particular user. So as we go through that, we're talking about just a CPU, and really talking about one core. But now, as we talk about multiprocessors, we can divide that so we have several cores each doing those things. And we want to make sure that we have asynchronous synchronization so we can process each of those separately without confusing each other and prevent all those collisions. So you can see that kernel has a lot of things to do and a lot of things to manage, and it takes quite a bit of effort to make sure everything's separate and secure. And so with that, I'm going to stop. You have some questions, 3 or 4 questions to answer, and you can submit those online. Thank you very much. See you next time.